Now we are going to see to prove how to prove that t of uk plus 1, t of uk plus 2, and so on, t of un is linearly independent. So to show that linearly independent, we will consider this summation I is equal to k plus 1 to n ci t of ui is equal to 0. Now we know t is a linear transformation, so we can take summation and constant inside the t. Now this summation k plus 1 to n we can split as I is equals to 1 to n minus I is equal to 1 to k is equal to 0. Now t is a linear transformation, so that means we can write down this one as a t of I is equals to 1 to n ci ui minus t of I is equals to 1 to k ci ui is equal to 0. Now again we can interchange the summation and constant outside the t. So we know that ui is nothing but a ui from 1 to k is an element of kernel. So that means what? That t of ui from 1 to k must be 0. So only the remaining thing is what? T of ci I is equals to 1 to n ci ui is equals to 0. Now t is a linear transformation, and we know this t of this thing is 0. That means what? The element has to be 0. So this can be written as I is equals to 1 to n ci ui is equals to 0. Now we know ui, u1, u2, un is nothing but a basis of our domain. So this means that this has to be linearly independent. So that means what? Ci must be 0 from 1 to n. So this implies that from k plus 1 to n the element also 0. So this means that t of uk plus 1, uk plus 2, and so on, t of un is linearly independent. This implies that the dimension of our image of t is what? N minus k. Now if we add the dimension of kernel and dimension of image, so this becomes k plus n minus k, which is equal to n, and this is nothing but a dimension of our domain u. This implies dimension of the domain is equal to dimension of kernel of t plus dimension of image of t.